So good afternoon, everyone. Welcome to the June mini-school of the National Institute of Theoretical and Computational Sciences. My name is Francesco Petruccione, and I'm the interim director of NITheCS. Today, I have the big pleasure of introducing to you Professor Sunandan Gangopadhyay. I'm particularly happy because he just reminded me that he was the very first postdoc of NITheP back in 2008. Yeah? So he's been following NITheP from the very beginning and certainly helped shape it at the very beginning. So Sunandan, we are very grateful that over so many years, you kept the relationship with NITheCS going, NITheP and now NITheCS going, and you keep supporting us and engaging with us. Yeah. Sunandan did his PhD at the Bose National Centre for Basic Sciences in Kolkata back in 2008, and afterwards he came to South Africa, where he joined NITheP in Stellenbosch. When he left Stellenbosch, he was appointed as a lecturer in the physics department of West Bengal State University in 2009. He visited back NITheP in 2013, yeah, and is now his associate professor at his alma mater at the Bose National Centre for Basic Sciences in Calcutta. And can you manage? He's working in theoretical. Can you say theoretical high energy physics and surroundings, yeah? and today and in the next weeks he will share with us a short introduction to path integrals approach, to the path integral approach with applications in quantum mechanics and quantum field theory. Yeah. So Sunandan, thank you so much for being with us today.
Thank you.
We are all very much looking forward to your lectures. Yeah. While I ask you to start sharing your screen, if you want, yeah, just a reminder to the participants who maybe use the Q&A facility at the bottom of the Zoom screen to ask questions. And maybe at the end of the talk, if you want to ask a question in person, just raise your hand and I will give you the right to talk. Yeah. So Sunandan, please, people are here to listen to you and not to me. Thank you very much.
Thank you, Professor Petruccione. Thank you for this wonderful introduction. And also, it is a pleasure to give this webinar, this short mini school. And the topic that I would be telling you in this mini course, I hope I'm audible to everyone. So
yes, we can hear you clearly, see you clearly, and we can see your
okay. And my screen is also visible, right?
Yes,
so,
yes.
So the topic that I would be trying to tell you in this mini course is on path integrals in quantum mechanics and quantum field theory, and possibly I can also tell you something about its connections with statistical mechanics. And we know that path integrals play a very important role in various branches of not only physics, also in economics and various other disciplines. So let me start with this course. So first of all, before going to path integrals proper in quantum mechanics, I shall try to tell you or give you a small primer, on quantum mechanics. So here, we know that time evolution, so the pointer is also visible, right? You can see the pointer. So time evolution operator transforms the quantum mechanical state at an earlier time t1 to a future time t2 in the following way. So if psi t1, ket psi t1 is the initial state ket of the system, then u hat t2 comma t1, this is the time evolution operator. This time evolution operator basically takes us from the initial state ket psi t1 to the final state ket psi t2. So t2 is a later time. That is why I've mentioned that t2 is greater than t1. and you had T2 comma T1, this is the time evolution operator. And clearly for a time independent Hamiltonian, we know that you had T2 comma T1 is basically given by this following expression, e to the power of minus I by h bar Hamiltonian operator multiplied by T2 minus T1. So T2 is greater than T1 here. So T2 is a later time and T1 is an earlier time. So this is the form of the time evolution operator when the Hamiltonian is time independent. And since T2 is greater than T1, you had T2 comma T1, this time evolution operator can also be written in the following way. It is some theta function T2 minus T1 e to the power of minus I by h bar h hat T2 minus T1. So you should not confuse this notation h hat as function of T2 minus T1. Rather, it is the Hamiltonian, which is time, which is an operator, which is time independent, times T2 minus T1. So you can write, what I'm saying is that you can write the time evolution operator you had T2 comma T1, which is given by this. You can also write it in this way. The reason is very clear. This theta is T2 minus T1 is a theta function, Heaviside step function or Heaviside function. So this is equal to 1 when T2 is greater than T1, and when T2 is less than T1, this theta function is 0. So we know that T2 is greater than T1 because T2 is a later time. Therefore, this function is actually 1. But you will see the need of this function very soon. And the form of this time evolution operator, which follows from the Schrodinger equation, right? This is the time dependent Schrodinger equation, I h bar del L t acting on ket psi t, that is equal to h hat ket psi t. So if you have this time dependent Schrodinger equation with h hat being the Hamiltonian operator and also being time independent, then you can actually construct the time evolution operator and it comes out to be of this form. Now you can do a very small calculation. The calculation is very straightforward. With this form of the time evolution operator, you act IH bar del LT on both sides of this equation. So you have this equation now. You have this equation. This is our equation. So on this equation, what we do is we act on both sides of this equation with IH bar del LT. And let's see what happens. So if you IH bar del T, but this time T is the later time T2. So if we do that, then what we find is the following: IH bar del T2 acting on U hat T2 comma T1. Just a minute. Just so IH bar del T2 acting on U hat T2 comma T1. So if you do this, and now this IH bar del T2 acts on the right hand side of this equation. So if you do that, if you act with IH bar del T2 on the right hand side, then del T2 acts first on the theta function. The exponential, this operator remains unchanged, and then this del T2 acts on this operator, and this theta function remains untouched. So going to the next step, del T2 acting on this theta function, theta T2 minus T1, is nothing but, you know that it is the delta function, it is the Dirac delta function. So this is a very standard relation that when you differentiate a theta function with theta function of say x or say time t and differentiate it with respect to time t, then it gives you a delta function. Derivative of a theta function is a delta function. So the first term is a Dirac delta function, and now you have this term, the exponential operator, and then when you differentiate the exponential operator with respect to time t2, the Hamiltonian comes down along with this factor of minus I by h bar, and you have this. So now it is quite straightforward. So what we have is the following: you have IH bar del 2 Dirac delta T2 minus T1, and on top of that this IH bar, and also you have this this operator, I think. Just a minute. So along with this, I think I've missed this factor here. There should be a factor of this exponential operator sitting over here. And then IH bar minus IH bar, this basically cancels to give you a plus, then this theta function, then the Hamiltonian operator times this exponential operator once again. So what we have is the following now. We have IH bar Dirac delta T2 minus T1 plus H hat acting on U hat T2 comma T1. So from this particular thing, if you take this term on the other side of the equation, we have IH bar del T2 minus H hat acting on this unitary operator is basically equal to IH bar Dirac delta T2 minus T1. So what this small exercise basically says is that this time evolution operator is basically like a Green's function. Although it is not a function, it is an operator, but it is you can call it to be a Green's function, because when you take matrix elements of this operator, this object becomes this object in particular state gates. This will become a number, and that number, when this operator acts on that number, it is basically a Dirac delta function, and therefore this is nothing but the Green's function. So determining this operator, so our aim is to determine this evolution operator U hat T2 comma T1. So determining this operator is equivalent to finding its matrix elements in a given basis. For example, in the coordinate basis, we know that we have the ket Q, and operator Q hat acts on ket Q to give this. So this ket Q is an eigenstate of this operator. One can write the matrix element of this time evolution operator U hat T2 comma T1 in this coordinate state kets. So this is Q1 ket Q1, and this is bra Q2. And this is, once you calculate this matrix element, this is basically a function, and that function we call it to be, this notation just tells you that we are just calling this function to be some function U, Q2 comma T2 semicolon Q1 comma T1. So our aim is to actually find this function. And this function actually owes its origin from the time evolution operator. Knowing this function U of Q2 comma T2 and Q1 comma T1 completely gives the time evolution of the wave function in the following way. So if you have the initial wave function psi Q1 comma T1, and you have this function U of Q2 T2 and Q1 T1. So what this function does is the following. It takes us from this wave function at Q1 at the position Q1 at time T1 to the wave function psi at the position Q2 at time T2. So the role of this function U, which actually comes from the time evolution operator, the role of this function U is basically to propagate us from one point at a particular time to another point at a particular time. So it basically takes this wave function psi at Q1 T1 to the wave function Q2 comma T2. So this function is like a propagator. So in the literature, this is also known as a propagator or kernel or Green's function. So there are many names for this function, and this is a very important function. So this was the quantum mechanics primer that I wanted to begin with. So now let us move on further, and let us see how path integrals, what path integrals basically means. So basic quantity of interest in quantum mechanics is the probability amplitude. Is the probability amplitude of transition to evolve from one Q eigenstate to another Q eigenstate in a time capital T. So this is the basic quantity of interest. So I have just now shown you in the previous slide this object. So this is basically the object that is of interest to us. So I've written the same object once more in the next slide. So here, what I'm saying is that this Qi is this is a coordinate state base, or basically we can, let me just write it down. This is a base state. This is a base state, and I denote it by, this is the initial base state Qi, and this is the final base state. And this is the time evolution operator that I've been talking about, e to the power of minus I by h bar Hamiltonian times time capital T. So this is the quantity of interest that we are looking for, and these base states, these are basically in the Schrodinger picture. So you should remember one thing, that in the Schrodinger picture, the state states are time dependent. The base states, which are these Qi's, these are time independent, and the operators in the Schrodinger picture, they are basically time independent. Okay. And in the Heisenberg picture, the state states, these are time independent. The base states are time dependent, and the operators are also time dependent. So in the Heisenberg picture, we have equations of motion for the operators, which are called the Heisenberg equations of motion. So here, this is basically the Schrodinger picture. And now you can go from the Schrodinger picture to the Heisenberg picture, where the base states are time dependent. So you can write down the same expression in the following way, Qi, 0. And so this expression that we are after, so this same expression can be written as the overlap of Qi, 0 with Qf, T. So this state state basically tells you that this is a state state at Qi, at the position Qi, initial state state at time t is equal to 0, and this is the final position at time t. And this base state in the Heisenberg picture, which are time dependent, are related to the base states in the Schrodinger picture, which are time independent, in the following way. So that can be easily seen from this expression. You can easily find out that Qt, ket Qt is basically e to the power of plus I by h bar Hamiltonian operator time t ket Q. So there is a interesting thing here. You can see that usually state states, when you have an initial state state and when it evolves to some final state state at time t, the evolution operator is e to the power of minus I by h bar Hamiltonian operator times time t. But here it is, the minus sign is not there. The base states are this base state, which is time dependent, is related to the time independent base state in this following way. The minus sign is not here. So this is something very important, and this you can easily figure it out yourself. If you have some problem with this, I can answer this at the end of this lecture. So let us now move forward. So as I mentioned to you, that our main aim is to write this in a particular form. And the particular form is the form that we call a path integral or a functional integral. So let us see how we can do that. So for that, let us go to this following simple picture. So here you can see that our aim here, so this is the position of the particle Qi. Say a particle is moving from Qi at time t is equal to 0 to the position Qf. So this is Qf at time t is equal to capital T. So what we do is we make small time slices, equal time slices. So from time t is equal to 0. So this is the time axis. I have given this arrow for the time axis, and this is the position axis, right? And here, from this point, the particle, I have made some equal time slices, and from here, see, the particle can go to this time slice like this. This is one possible path. So it goes from here to here along this dotted line, and from here to here, and then from here to here. It can go from here to here also, anywhere it likes. So it can go from here to here, then from here to here, and then to the final destination. So you can see that going from this point to this point, the particle can take several paths. It can take infinitely, in principle, it can take infinitely many paths. Although relativistically it is not possible, but non-relativistically there is no problem. From this point at time t is equal to 0 to go to this final point at time t is equal to capital T, it can take infinitely many paths. So So that is why you can understand that how the notion of path integrals actually comes. So it is basically a sum over all possible paths that a particle can take in going from some initial point at some time t is equal to 0 to some final point at some time t is equal to capital T. So it is the sum over all possible paths, or in the literature it is also sometimes called sum over the histories. So now if we move further forward, what we need in developing the path integral is another relation which is known as the completeness relation. So this equation 3 is the completeness relation. So it tells us that integral from minus infinity, so this to this, dq ket q comma t bra q comma t is equal to the identity operator. This is a completeness relation that we are all familiar with in quantum mechanics. And I would suggest that I would just tell you to do a small exercise at this point. From this relation, you please try to show that this is also satisfied. So this was in the Heisenberg picture, the completeness relation in the Heisenberg picture, and this is the completeness relation in the Schrodinger picture. So you can immediately show by using equation 2. If you just use equation 2 and equation 3, combining equations 3 and equation 2, you can easily show that you can derive this completeness relation. So this is just a small exercise. Now we move forward further. So what I have done is we have divided the time interval into n equal steps. And we are calling each time slice, we are labeling each time slice as Tm, T suffix m, which is equal to some number small m times epsilon, where epsilon is the width of each of the time slices. So these are equal time slices. So epsilon is the same for each time slice, and that is given by the total time interval capital T, which the particle takes from going from the initial time to the final time, divided by the total number of steps, total number of time slices that we have made. So n is the number of time slices. So what we would like to do at the end of this calculation that I'm going to show you is that I would like to take the n going to infinite limit, which actually means that for a fixed time capital T, if n goes to infinity, then epsilon goes to 0. And also Tn, so if I put small m is equal to capital N, then T capital N is basically equal to the total time interval capital T, and that is equal to n times epsilon. And T0, if I put small m to be equal to 0, then T0 is the initial time from where the particle starts. So T0 is equal to 0. So you should just keep in mind this small figure, and everything will be straightforward now. Everything follows very easily now. So our aim is to calculate this overlap, which is the overlap of qi comma 0 with qf comma t. So in order to calculate this overlap, or rather than saying calculate, we want to cast this overlap in a particular way. And that is the essence of this path integral formulation of quantum mechanics, which is obviously an alternative formulation of quantum mechanics. So the essence of the calculation is as follows. What one does is introduce these completeness relations, this equation 3, the Heisenberg, the completeness relation in the Heisenberg picture, in that overlap. And one has to introduce it in each of the time slices that appear in that figure that I've shown you. So if you introduce, so at the T1 time slice, so when small m is equal to 1, you introduce this completeness relation. So that gives you Q1 T1 ket, and then bra Q1 T1, and then you do it at time T2. So it will be ket Q2 T2, bra Q2 T2, and so on. And you keep on doing it till the n-1th time slice. So at the n-1th time slice, you have dq n-1, and so you have this particular matrix element or overlap, which is nothing but qf comma t with qn-1 and tn-1. So this is the ket and this is the bra. So this is the completeness relation. So you introduce, so basically what you are doing is you are introducing identity operators. So these completeness relations are basically identity operators, and you can freely introduce the identity operators anywhere you want. So since these are identity, and identity is basically integral of dq ket q bra q, so you introduce these relations in that overlap, in this overlap. So if you do that, Now, this expression can be written in a very simple way. So this expression now becomes integral minus infinity to plus infinity dq n minus 1 to dot 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 d to dq1, and then you have this product of all these overlaps. So this is one overlap, this is another overlap, and so on. So there is a product of overlaps that we encounter. So you can write all those product of overlaps in the following way. It is basically m is equal to so this will be m is equal to 1 to, let me just correct it at this point. So this will not be 0 because the no, it will be 0. I think it is completely correct. It will be 0. Just a minute. So it will be the overlap of okay. So it will be the product of these overlaps. So you can see that this expression is basically equal to this expression. So you write it in a more compact form using this product notation. So it goes from m is equal to 0 to n minus 1. So that means that it is q0 comma t0. The next term is q1 comma t1, and so on. And ultimately it goes to, when m is equal to n minus 1, you get this term. This is the term that you get. Now, all this is in the Heisenberg picture. Now we want to go to the Schrodinger picture. And in the Schrodinger picture, we want to calculate a overlap, a test overlap, which is of the following form, which is QM-TM with bra QM plus 1 comma TM plus 1. So we want to calculate this overlap. So if we can calculate this overlap, we will just plug it, put it back into this expression, and then move forward with our calculation. And in order to calculate this overlap, what we do is the following. We now go back to the Schrodinger picture. So we break these base cases in the Heisenberg picture to the base cases in the Schrodinger picture. So when we break Qm comma Tm, we get e to the power of I by h bar Hamiltonian operator Tm ket Qm. And on the bra, on this side, for this Qm plus 1 Tm plus 1, we can write it as bra Qm plus 1 e to the power of minus I by h bar Hamiltonian operator Tm plus 1. So, this follows. So what we have done is we have translated from this base case in the Heisenberg picture to the base case in the Schrodinger picture. Now you can combine these two exponentials. It is easy to combine these two exponentials because the same operators lie on the sit on the exponent. So you can combine these two exponentials in the following way. Let me just. So if you combine it, you will get h hat with Tm plus 1 minus Tm. And now I write this Tm plus 1 minus Tm. You remember that Tm, we had written it as T suffix m was equal to m times epsilon. So Tm plus 1 minus Tm is basically epsilon. So what we get is e to the power of minus I by h bar Hamiltonian operator epsilon times epsilon. So this is the time interval between two time slices. So far, so good. Now what we do in the next step is the following. We introduce the completeness relation, which are not written here, but let me just write it down here. We introduce the completeness relation for the momentum states. So this means we introduce another identity operator. So this is the completeness relation for the momentum states. So, and this is an identity operator. So we are free to introduce this thing. So what we do, we introduce an identity operator here. So suppose you introduce it over here, and in place of this identity operator, just plug in this expression. So if you put in this expression, this then leads us to the following integral. Integration from minus infinity to plus infinity, dPm, overlap of Qm plus 1 with the momentum state Pm, then the following matrix element, which is bra Pm e to the power of minus I by h bar Hamiltonian operator epsilon ket Qm, right? So our next job is to calculate this overlap. And this overlap is very simple. We all of us know this is straightforward from quantum mechanics. I shall write it down later, but let us calculate this overlap first. So we need to calculate this matrix element, which is the matrix element of this operator between the state Qm and this state Pm. So in order to do that, I mentioned at the beginning that the time intervals, the time slices that we are taking, we want to take the n going to infinite limit. So we want to make infinitely many time slices from time t is equal to 0 to time t is equal to capital T. And therefore, since capital N is infinity, therefore this small epsilon actually tends to 0. The time interval goes to 0. So what we can do is make an expansion of this exponential operator. So if you make an expansion of this exponential operator, the first term will be, since this is an operator, so you can expand it in a Taylor series or a power series. So the first term will be the identity operator. The next term will be minus I by h bar Hamiltonian operator times the epsilon, and then terms which are of order epsilon square. So from this term, from the identity operator, this basically gives us overlap of PM with QM. The next term gives us, you can pull out minus I by h bar epsilon because this is a number. So you can pull it out of this matrix element. So this comes out. And then what remains is the overlap of this Hamiltonian operator between PM and QM. And then term plus terms of order of epsilon square. And this Hamiltonian operator, as we always all know, that this is a function of the operators P hat and Q hat. So this you can then write it down as this. Once again, I write just this down once more. And this Hamiltonian operator, since this is a function of P hat and Q hat, so, and these momentum eigenstates, these are basically eigenstates of the of this Hamiltonian operator. So we assume that these momentum eigenstates are eigenstates of this Hamiltonian operator. So what you can write is the following, because this Hamiltonian, for the simple case, for example, if you take it to be p square by 2m for the free particle, this will just act on this state ket and it will become a number. It will become p square by 2m, ordinary number. So you can write this Hamiltonian operator, which was a function of these two operators P hat and Q hat, in the following way. It now has become a function. It is a function of PM and QM, and then PM, bra PM and ket QM, and then these terms of order epsilon square. This basically implies that you can write down the overlap QM plus 1 TM plus 1 with QM TM in the following way. If you put in all these expressions back, the expression that we are going to land up with is the following one. This is the expression, which is an integral over dpm, and you have this term as common because this term has come out from here also. You can take this term common. So you just pull it out, and what you have is the following expression. So this is the expression that we have. And from here, you can write this down as, see, the term in the bracket that you have over here, you have PM QM, and this you have PM QM also appearing here. So you take this term outside the bracket. So the resulting expression is of this form. So this is bra QM plus 1 PM, then ket PM, bra PM ket QM, and times this function in the brackets. And now what the important step that one has to carry out is the following. Since epsilon is very small, infinitesimally close to 0, so it is infinitesimally small, so it is very close to 0. So this term that you have here, we can re-exponentiate it. We can again write it down in the form of an exponential term. So what we do is that we write this full term as e to the power of minus I by h bar Hamiltonian PM comma QM times epsilon, and then you have these two overlaps obviously sitting over here. And now what we do is we need to write down the expressions for these two overlaps, of the overlap between the momentum states and the position states. So if you write down those overlaps, the overlaps between the momentum states PM and QM is of this following form. So you just put these forms of the overlaps in this expression, and then what we shall get is the following. So this is the final expression that we have. It is integral dpm by 2 pi h bar e to the power of minus I by h bar bracket Hamiltonian. This is no more an operator. This is now a function. This is a function. The Hamiltonian is a function of PM and QM times epsilon minus PM bracket QM plus 1 minus QM. So the net result of doing this whole calculation is that the overlap of QM TM with QM plus 1 TM plus 1 is nothing but this final expression. This is the expression that we have got. Once we have got this expression, the rest is quite straightforward. What we shall do is we shall straight away pluck this expression in the initial form that I had shown you earlier. Let me go back to the initial form. How many minutes do I have? How much time do I have? So time? So what we are half an hour. 1 ঘন্টা. Okay. So what we are going to do is we are going to put the expression that we have calculated, the overlap of QM/TM with QM plus 1 TM plus 1. We have calculated this expression. We shall put it back here, and then we shall write down this full overlap that we are after. We want to write this expression in a particular form. So for that, we have calculated this expression now, and we shall put it back over here now. If you put it back over there, then what we shall get is the following. So this particular overlap, so QF comma T with QI comma 0, QI at 0, this overlap is basically integral product dQy. You remember that there are n-1 Q integrations, and the Q integrations, these are from dQ1, dQ2 to dQn-1. So I have written it from I is equal to 1 to n-1. But the number of momentum integrals start from n is equal to 0 to n-1. So there is a momentum integral more. In case of the momentum integral, there is one integral more than the position integrals. So it starts from m is equal to 0 to capital N-1, and then integral minus infinity to plus infinity dpm by 2 pi h bar, and then you just have this expression that we have calculated just now. And these are terms of order epsilon square. And now you can arrange it write it in a nice form. You just open these product things. So you just open it up, and if you open it up, you will find that you can write the above expression in the following form. It can be written as dpn-1 by 2 pi h bar. With each momentum integral, there is a 2 pi h bar in the denominator, and then you have dqn-1, and it goes on dp1 by 2 pi h bar dq1, and there is one extra momentum integral which is dp0 by 2 pi h bar, and then you have this expression. And this, now you look at the expression inside this summation, and all this overlaps, this summation, I hope you can understand why this summation over in the exponent comes, because we have a product of overlaps, and all those expressions for each overlap, it just adds up in the exponential. It keeps up adding on the exponential, and that is why we have the summation. It goes from m is equal to 0 to capital N-1. And now this expression inside the summation, this expression, you can write it in the following way. You can take the epsilon common, and then it becomes HPM QM minus PM QM plus 1 minus QM by epsilon. And then this term, which is of order epsilon square, now becomes order of epsilon, because we have taken an epsilon out. Now in the n, capital N going to infinite limit, so the number of time slices that you have made is infinite. Epsilon goes to 0, and in that limit, you can see that you can write this summation. This summation becomes, you can write it as an integral from 0 to the total time capital T. This epsilon becomes equal to dt, and this qm plus 1 minus qm by epsilon, this becomes q dot, and therefore you can write this in a very compact notation. You can write it in the following way. You can write it as integral some bracket. So this is a different notation. This is called a functional measure. It is just a shorthand notation for the thing that you have written here. So this thing can be written in a shorthand notation in the following way. So this is dp, this is dq, and then you have put a bracket, and then you put these things here, qi comma 0, qf comma t. This basically tells you that the particle starts from qi at time t is equal to 0, and it ends up at qf at time t is equal to capital T. So these are like the boundary conditions for all possible paths. See, all possible, the particle can go from qi at time t is equal to 0 to qf at time t is equal to t, capital T. So it can take infinitely many possible paths. So that is why it is called path, a sum over all histories, or a sum over all possible paths. But every path has to start from qi at time t is equal to 0 and end at time position qf at time t is equal to capital T. So these are the boundary conditions. All the paths has to obey this boundary condition, and therefore you put these boundary conditions here in this expression. And then the exponential part, it basically translates to the following expression. It is e to the power of I by h bar integration from 0 to capital T dt t q dot minus h p comma q. So what we have done is that the most important expression that we are after in quantum mechanics, we always want to calculate this overlap, because this is basically the probability amplitude of transition for a particle to go from position qi at time t is equal to 0 to position qf at time t is equal to capital T. So this is the probability amplitude, and if you want to amplitude of transition, obviously from qi to qf. And this is the important quantity that we want to calculate in quantum mechanics. And now, and the way we do it in quantum mechanics is by solving Schrodinger equation. But now you have an alternative way of doing it. You have formulated this important quantity that we want to calculate in quantum mechanics as a sum over all possible paths that the particle can take while moving from qi to qf, from time t is equal to 0 to time t is equal to capital T. So this notation that I've given is basically tells you that it is a summation over all possible paths. These are called functional measures, and this particular integral is called a functional integral or a path integral. So this is basically the path integral formulation of quantum mechanics, and the main game here is to calculate this functional integral or path integral. And if you can calculate this path integral, you actually know this overlap. And if you know this overlap, this overlap basically is, as I told you, that this is basically the Green's function or the kernel or the propagator. It given a wave function, if you know the form of the wave function at a time at some initial time, this probability amplitude of transition is like a propagator. It takes you from the initial wave function and gives you the final wave function. So the main aim, so now you don't need to work with any operators, because this amplitude is totally expressed in terms of some object where there are no operators. Everything is written in terms of some functions, and this integral is not an ordinary integral. This is a functional integral, which basically tells us that this is the integral over all possible paths that the particle can take. And not only that, this is the phase space path integral, because you can see that you have all possible momentum paths also, and all possible momentum p's also involved in this functional integral. So this is a phase space path integral. So now let me just make a small comment here. So I've just written down this phase space path integral once more in a very neat form. So this is the expression that you should have here in your notebooks. The integral runs over all paths pt and qt in phase space with given qt and q0 in the epsilon going to 0 limit. This is called the phase space path integral or the Hamiltonian path integral. Also, this is, as I mentioned, this is the functional integral, and this basically means this is the sum over phase space paths weighted by e to the power of I by h bar s, with s being the action in the Hamiltonian form. So you see that this particular thing, this is basically the Legendre transform of the Hamiltonian function. So this is some sort of a Lagrangian, and Lagrangian times dt integral over L dt, and when you integrate it, it gives you the action. But this is the action S in the Hamiltonian form, because the Hamiltonian form is involved here. So this is called the phase space form of the path integral. Now our aim is to go to a more familiar form of the path integral, and for that what we shall do is we shall make a stationary phase approximation. And what is this approximation? In this approximation, what we say is that the integral, this path integral, is dominated by the point of stationary phase. So what do you mean by that? So from this action in the Hamiltonian form, so this is, as I mentioned, this full thing, this expression e to the power of I by h bar, the rest of the thing is the action in the Hamiltonian form, this integral 0 to t. So the stationary phase approximation basically tells you that this path integral over P and Q, this is dominated by the point of stationary phase. So what you basically do is you calculate the classical equations of motion, and then you evaluate this path integral on the classical equation of motion, and the stationary phase approximation basically tells us that that will be the dominant contribution. The contribution coming from the evaluation of the path integral when it satisfies the classical equations of motion, that will give us the dominant contribution of the path integral. And there will be obviously other terms, but those terms will be suppressed, or those terms will be small compared to the dominant contribution. So that is the stationary phase approximation. And in that approximation, so since we are saying that we want to calculate the point of stationary phase, and the point of stationary phase is basically given by this form, del P. So you basically maximize the exponent. So del P of PQ dot minus HPQ, and you equate it to 0. When you calculate this expression, del P of PQ dot gives you a Q dot, and the next term is obviously del H del P. And therefore, from here, what we get is the following. You call this function, the derivative, partial derivative of this Hamiltonian with respect to the momentum, you call this sum to be some function f of PQ, and therefore you get Q dot to be equal to f of PQ. And now, from this equation, if you invert P in terms of Q and Q dot, you will get P to be equal to G of Q comma Q dot. And therefore, since P is now related in terms of Q and Q dot through this function G, now you can write this PQ dot minus HP comma Q in the following way. This is basically, you can now put the value of P here in this expression. So that gives us GQ comma Q dot times Q dot minus H. Again, in place of P, you put GQ comma Q dot and then comma Q. And this, you notice that now in the stationary phase approximation, when the momentum gets related to Q and Q dot, this expression PQ dot minus HP comma Q, this is basically totally a function of Q and Q dot. And that function, we call it to be the Lagrangian or some function L. And now we are ready to write down the Lagrangian form of the path integral, or the configuration form of the path integral. So QF comma T QI comma 0, this is basically the phase space form of the path integral. And to now we incorporate the phase space approximation, and in the phase space approximation, P is related to Q and Q dot in this way, that is P is equal to G, some function G of Q and Q dot. So you incorporate the way to incorporate the phase space approximation is to introduce a delta function, so that this relation that P is equal to G function of Q comma Q dot is enforced. So that relation is enforced through this Dirac delta functional. This is not a function now, rather this is a Dirac delta functional. So you have this functional integral, functional measure dp dq, qi0 qft, Dirac delta functional, which enforces the constraint, or which enforces the stationary phase approximation that now P is related to Q and Q dot, and times this e to the power of function. And this Dirac delta, with this Dirac delta functional, you can now carry out the momentum, the path integral, the momentum path integral, the momentum functional integral. And if you carry out the momentum functional integral, what we are left with is with the configuration, the position part of the functional integral. So it gives, so we have dq running from qi0 to qft. So this tells us that all possible paths start at qi at time t is equal to 0 and end at qf at time t is equal to capital T. And you just put, wherever you have P, you just put the form of P to be equal to GQ comma Q dot, and you have this expression. And this expression is purely a function of Q and Q dot. And that function, we know, if any function which is a function of the generalized coordinates and the generalized velocities, Q dots, this is the Lagrangian function. And therefore you have LQ comma Q dot and integral over 0 to T. And this LQ comma Q dot integral 0 to T, this is the action functional. So this is SQ, and this is and then you have the path integral over all possible paths dq, which with the following boundary conditions qi0 qft. And this form of the functional integral, or the path integral, is called the Lagrangian path integral. So what we have learned now is that we can come from the phase space form of the path integral to the Lagrangian form of the path integral by making a stationary phase approximation, which basically tells us that the momentum path integral is dominated by the point of stationary phase, which basically means that you have to impose the classical Hamilton's equations of motion, and when you impose that, it basically gives us that it basically tells us that the momentum is related to q and q dot. Enforce that condition on the phase space path integral, you will end up with the configuration space path integral, which is this expression. So this is the Lagrangian path integral, the integral over all possible paths qt in configuration space, weighted by the factor e to the power of I by h bar s, where now s is the Lagrangian action, not the Hamiltonian action anymore. So Lagrangian action basically means that it is the integral of the Lagrangian over time t. Let me go to the classical limit quickly. So in the classical limit, to go from quantum mechanics to the classical mechanics, we know that the limit is the Planck's constant going to 0. So h bar going to 0 limit is the classical limit. In the classical limit, the path integral that I've just written down, the configuration space path integral or the Lagrangian path integral, is basically dominated by the paths of stationary phase. Once again, this configuration space path integral is also dominated by the paths of stationary phase. What do we mean by that? It is the classical path. So in the particle in going from qi0 to qi at time capital T, t small t is equal to capital T, there are infinitely many paths. But which path will give you the maximum contribution to the path integral? And it surprisingly, it's not a surprise also, it is a nice thing that the dominant contribution actually comes to this path integral from the classical path. So this is something very interesting. And that path is basically the path of stationary phase. And that is given by delta S, delta QT is equal to 0. So this basically means that this is a functional derivative, delta S by delta QT. So if you want to know what functional derivatives are, I can tell you later, but this is this functional derivative of the action, because this is not an ordinary derivative, because now the action is a functional of Q. So you have to take functional derivatives. You need to know how to take functional derivatives. So the equation of motion, the classical equation of motion, is basically given by this following equation: del S del QT is equal to 0. This is the classical equation of motion. And in the h bar going to 0 limit, you will the integral will be dominated by the paths of stationary phase, and that will lead us to the following equation of motion, which is basically the classical equation of motion. Now let us see a particular case where we can do some concrete calculation. By concrete calculation, I mean that we can do we can carry out these path integrals. So let us take a particular example. Let us consider this, that the Hamiltonian function that we have is given by p square by 2m plus v function of q. So let's write down the phase space path integral once more, and with the following form of the Hamiltonian. So this is, all of us know that this is the non-relativistic form of the Hamiltonian function. So this is the phase space form of the path integral. This is in the shorthand notation, and you know that this functional integral, the sum over all possible paths, the integral over all possible paths in phase space, basically actually in longhand, it actually means this expression. This is, by this expression, we actually mean this expression. So let us concentrate on this expression. And with the non-relativistic form of the Hamiltonian, you can see that this h, pm, qm is given now by this. So h, pm, qm will be pm square by 2m. This m should not be confused with this m. This is a notation. I should have written this down as mu or something like that. So this m basically denotes the mass of the particle, of the non-relativistic particle. So h, pm, qm is now pm square by 2m plus v qm. So with this non-relativistic form of the Hamiltonian, we can see that if you put this non-relativistic form of the Hamiltonian here, all these momentum integrals are basically Gaussian integrals, Gaussian momentum integrals. And Gaussian integrals are very easy to carry out. So what we shall do is, we shall carry out a generic Gaussian integral. So let us carry out the NITheP integral. So the NITheP integral, from this dirty expression that I've written down here, let me just write down one generic integral, which is the mth integral over momentum. So that integral is of this following form: dpm by 2 pi h bar e to the power of minus I by h bar small epsilon, and then you just write down the Hamiltonian function here. And you can see that this is a Gaussian integral, although with a catch. usually in Gaussian integrals, you do not have imaginary numbers here sitting, but here you have an imaginary number, a complex number sitting here, but still you can actually calculate this Gaussian integral with the standard formulas of Gaussian integrals. It can be done. If you have any questions, I can clarify this later. So you can, if you carry out this Gaussian integral, I have given all the steps here. So you just, the way to do this Gaussian integral is to just complete the square. You just complete the square. This is a simple exercise. You complete the square, and then you apply the formula of Gaussian integral, which is nothing but, let me just write it down here. It is integral minus infinity to plus infinity e to the power of minus ax square dx is equal to pi by a square root, so pi by square root of pi by a, with the only restriction that real part, this a can be a complex number. This small a that I have written down here, this can be a complex number in general. So the restriction is that this result will hold only when real part of a is greater than 0. So if you apply this formula here, you will be able to compute this this integral, and the result is this. So you can see that the mth momentum integral can be carried out easily. And since one of the momentum integrals has been carried out, all momentum integrals can be carried out easily. So you just put in the expressions for the momentum integrals in this expression for the overlap qi0 qf comma t. If you put in the expression for the overlaps, I've written down all the steps in these notes. You can just carry it out yourself. What you will get is the following expression. From each of the mth integral, you will have a factor like this, and that is why you have a factor of n by 2, because there are n number of momentum integrals. So you have n by 2, this expression to the power of n by 2, and then multiplied by all position integrals dq1 to dqn minus 1 running from minus infinity to plus infinity, and then you have this expression e to the power of I by h bar epsilon summation n is equal to 0 to n minus 1, and then you have this expression that we have calculated. Now, once again, in the epsilon going to 0 limit, you can see that you can write this as qm plus 1 minus qm by epsilon. This can be written as q dot. And therefore, what it boils down to the following thing. You can write dq1 to dqn minus 1 running each of these q1s to qn minus 1 running from minus infinity to plus infinity. You can write it as a functional measure. This is the shorthand notation. So d capital D small q running, and the boundary conditions are qi comma 0 to qf comma t, and then e to the power of I by h bar integral 0 to t, and then you can see that this is m by 2 L dot q dot square minus vq. So that is nothing but kinetic energy minus potential energy, and it is also a function of q dot and q, and therefore this is a Lagrangian function. So this is L dt, and L dt in integral 0 to t is nothing but the action functional sq. So once again, for the non-relativistic form of the Hamiltonian, we can see that starting from the phase space form of the path integral, we can land up to the configuration space path integral without making any approximation. This is an exact result. So for the non-relativistic form of the path integral, the phase space approximation that we have shown earlier to go from the phase space form of the path integral to the configuration form of the path integral, now that phase space approximation is an exact result. It is no longer an approximation. It gives you the exact result in the non-relativistic Hamiltonian case. So this is one of the instances where you can calculate the momentum path integral exactly and land to the configuration form of the path integral. Now let me show you how much time do I have.
You have maybe a couple of minutes.
So would it be a nice place to stop here, or should I continue a little bit more?
No, I think this is probably a good place to stop, so that maybe next time we start with the new chapter, so to say.
Yeah. So next time what we can do is we can what I was aiming for is to calculate the path integral for the free particle case. So
perfect.
So in the next lecture I will start from the free particle. So
perfect.
I will show.
Fantastic. Yeah.
Okay.
And maybe we can give now the participants an opportunity. I see there is a question in the Q&A by Emil Roduner, and he asked: the Schrödinger equation is a deterministic equation that determines a trajectory. You obviously assume that your path does not need to follow this trajectory, but that you are free to choose your path. What am I missing?
Yeah, this is a nice question. So let me just go back to the picture, small picture that I have shown you. Let me go back to the small picture. In any case, I am going to share all these notes with you, and I
Yeah,
shall
no,
send
thank you very much. That's very kind.
Yeah,
We can post them on the website. Yeah.
Yeah. So, okay. So what I understand from the question is that you are basically troubled with the fact that when I have drawn this picture, so here I'm saying that this is the particle at time t is equal to 0 located at the position qi, and this is going to the position qf at time t is equal to capital T. And in going from this point, from this initial time to this final point to the, at this time capital T, I've drawn some paths, right? So these are these dotted lines are the paths. And the confusion that you are probably having is the following, that in quantum mechanics, we know that we have the notion of trajectories is not there. So you should take this picture with a pinch of salt. So it is not really, this is just an intuitive way of understanding what is going on. So these you should not take these drawings very seriously. So actually, these are basically clouds. So in quantum mechanics, there are no trajectories. Everything is in the form of a cloud. So we have the notion of trajectories is not at all there. But you should just try to understand these pictures very intuitively, that it is going from. So what I'm basically saying is that in going from this point, so let me just take the pointer to here. In going from this point to this point, the particle can take all possible paths. So these paths are like some clouds. And what is important is that in going from this point to this point, there is always a path. So this is not a very good drawing, but this is the path. So this is the classical path, say. So this is the classical path. So this is the path that the particle would have followed had it been a classical particle. So in quantum mechanics, we know that so there is always a classical path that the particle can take, but there are fluctuations about this path. And what I'm basically showing is nothing but the fluctuations about this path. So you can go from this path to this path about many possible paths. It is a sum over all possible paths. And these pictures are just intuitive pictures just for us to understand. Actually, these paths are not there in quantum mechanics. So these are all clouds. So I hope that I've more or less tried answered your question. Is it fine?
Thank you. I'm sure it is fine. Yeah. Are there other questions from the participants? And please, you're welcome to raise your hand, and I can quickly give you allow you to talk if you prefer, instead of writing it in the Q&A. Let's give a second participants to think, and if not, that will be just a sign that your lecture was very clear. Here we go. There is a question here, and I allow Hector to talk. Please, Hector, just unmute yourself and ask your question.
Okay, thank you, Prof. Can you hear me?
Yes, I can hear you.
In deriving the evolution operator, you made an assumption that the Hamiltonian was time independent. Does that causes you to lose any generality? And what would happen if the Hamiltonian were time dependent?
Oh, if the Hamiltonian, see, usually this is a very nice question. The important thing is that, well, see, our aim is the main aim here is to calculate these overlaps of qi, 0 with qf, t, right? And here we want to the whole formulation that I've been showing so far is based on the fact. This is a crucial assumption that you have correctly pointed out, is that the Hamiltonian is time independent. So this has to be there. Otherwise, this formulation will not hold, because you want to write down this ket q, t in the form e to the power of I by h bar Hamiltonian operator times t times acting on the ket q. And this will not hold good if the Hamiltonian is time dependent. So if the Hamiltonian is time dependent, then it will not be, this analysis will not go through. There also you can actually formulate the entire thing in form of path integrals, and what one has to do probably is to go to a density matrix formulation and then calculate everything by using density matrix, formulate the entire form of the path integral in the form of density matrices. So you write down the state ket in the form of as a density matrix. The state of the system is being represented by a density matrix, and then you try to formulate everything in terms of density matrices. So if the Hamiltonian is time dependent, so that is the way one should proceed. But probably if the Hamiltonian is time dependent, as you have correctly pointed out, then the main point is that you cannot write qt in the very simple form that e to the power of I by h bar Hamiltonian operator times t ket q. Rather, there will be an integral over this Hamiltonian operator now, because it is a time integral over the Hamiltonian operator. So let me just write it down here. So what I'm saying is that I cannot look at that. So what I'm saying is that the advantage of assuming that the Hamiltonian is time independent is the following, that you can write this in this form, right? But it is time independent in the sense that it has no explicit time dependence. See, this Hamiltonian operator is basically a function of p hat, which is a function of time t, and it is also q function of time t. So there is an implicit time dependence always in the Hamiltonian operator. But what I'm saying is that it has no explicit time dependence over time t, right? So this time dependence is not there. Had there been an explicit time dependence of the Hamiltonian operator, then this simple relation would not be true. This would not be true. And in place of that, what you would have got probably is there would be some kind of integral sitting over here, a time integral, right? So this will be some h hat time t and dt running from some time to some time, say 0 to t. And let me write down this tt prime and tt prime. So this will be something like this form. And then you can try and proceed in exactly this way and try to formulate this path integral formulation. You can try it yourself. This is a very nice question, but the analysis that I have shown today crucially depends on the fact that the Hamiltonian that we have considered has no explicit time dependence, but it has an implicit time dependence. The implicit time dependence coming through the dependence of the Hamiltonian on these p's and q's, on these momentum operators and q operators, which are themselves dependent on time. Is it okay?
Yeah, I think there was a thumbs up. We have one more question, Sunandan, by Akpan. And Akpan, please, you're welcome to ask your question.
Okay. Yes, please. Yes.
Akpan, please, you should have the right to speak. You're welcome to ask your question. Hello?
Yes.
Okay, he's gone. He's gone.
Oh, okay.
Okay, sorry. Maybe we can. Okay, there's another question here by Mahima. Let's try if this works, and then we should slowly come to an end. Mahima, please, you're welcome to ask a question.
Yeah, sure, sir. So this Hamiltonian being time independent, is it related to that Schrodinger deals with isolated system or not?
So you mean to say closed systems, right?
Yeah, sir.
Yes, closed systems. Yes, obviously. This formulation, this is totally a closed system. So,
yeah,
you know, for open systems, the master is already there. Professor Petruccione is the expert on open systems. So this formulation is totally based on closed quantum systems.
Sir, I wanted to ask you, due to closed system, this Hamiltonian is time independent.
Yes.
Or something.
Yes. It has no explicit time dependence.
Okay.
Absolutely. So an example of an open system would be putting an external magnetic field, which is a time dependent magnetic field from outside. So then the Hamiltonian will become explicitly time dependent, and then this formulation will not go through. You have to do something else.
Yeah, that thing. Okay. Thank you, sir.
Okay.
Okay, wonderful. Then Sunandan, I think we answered most questions except one. But maybe the person who wanted to ask that question, maybe by next week has sorted out audio problems. Yeah. So Sunandan, thank you so much. We recorded the lecture, so we will post it on our YouTube channel by, let's say, by latest tomorrow. And Sunandan promised to share the slides, so we will upload them on the website, so that you can all be ready for next week, second lecture on the topic. So thank you very much again.
Thank you. Will it be okay if I send you the lectures by tomorrow? The slides?
Yes. No urgency. No urgency. Thank you. Thank you very much. Then have a good rest of the day to all of you, and looking forward to see all of you again next week. Thank you.
Thank you.
Thank you very much. Bye-bye. Bye-bye.